equivalent to it. And so, yeah, it's just not doing anything. There's no path from state C to an accept state, so we just don't need it. Okay. La 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 la. Therefore, I mean, this whole thing is so dumb. This whole problem is so dumb because I really do believe that this machine ultimately just says you have to have an A or a B. I hope I'm reading that correctly, but I think that that's just right. Because if once you have an A, you're just automatically accepted. Once you have a B, you're automatically accepted, and then A and B are both effectively accept states. So just A's and B's, you just kind of waddle back and forth. This is just accepting anything, right? I mean, what doesn't it accept? Yeah, it just accepts everything. So nonetheless, we're going to follow the algorithm at least a little bit. So what should we do next? We need to delete a state. Okay, well I propose we delete state B. So if we delete state B, then I have my start state. I have here is A, and here is F. And, okay, so I got this, I'm just, once again, I'm redrawing kind of everything that was already there. So that's sort of it, right? A to A, yeah. Okay, so, but now, the lack of this state B is really tearing up my machine. So I need to reconstitute the functionality of B, and now I imagine all walks of length 2 that go through B. So could I go from S to A to B, for example? Oh, sorry, from S to B to A? Well, yes, definitely. From S to B to A, there was a path. That path was B, some number of B's followed by an A. So B star, A. Good. What about the path from A, from S to B to F? Yeah, that's also a thing. I can go through state S, the SBF path would now, because B is gone, means I can go directly from S to F with B star. And I guess lambda, but I leave that off. Okay. Now, what about A to F? Well, yeah, there's also going to be a new path from A to F through B. That path being B star, lambda. So there's going to be this B star thing. And then finally, the one that you might miss is the path from A to itself through B. And that path is, from A, I could do B star, A. So that means I'm going to have a new path, B star, A. So B star, A. Okay, so now introducing a kind of a cleanup step. What's going on here is I have S, my start state, I have A, and over here I have F, my lone accept state, and the paths from S to A are now A or B star A. The path from A to F is now lambda or B star, and the path from S to F is B star, and there's also a path from A to itself, which is A or B star A. Okay. Okay, and then I think the final step. I think this is going to be the last step, right? Although it might take me two lines to write it. What have I done? Is this wrong on my paper? Oh no. I think it is wrong on my paper. I'll just put this crap down. So now I'm going to delete state A. So this gives me S F, and maybe I need it to be over here. I don't know. I'll create more space if I need it. So cha-cha. Okay, well, what are the paths from S to F? Well, there's the old path. Yeah, I think I can just do this in one big go because really there's the old path, which is B star, or the new path. And what's the new path? The new path is, yeah, I need parentheses now, A or B star A followed by A or B star A parentheses star, then followed by lambda or B star. There it is. Okay, confidence that this is right, quite low. B star or A or B star A followed by A or B star A star followed by lambda. I guess that's maybe right. Okay, dare I try to, anyway, this is the algorithm, so I guess we're learning something. Dare I try to extract any meaning out of this? Machine. Whew. Well, a B will get it done, possibly followed by some number of B's. Alternatively, you could have an A followed by perhaps nothing and ending with nothing, or just like some B's and an A, or I don't know. I would wonder whether this whole machine, if I'm right, then this regular expression should be equivalent to the regular expression A or B star, because that's what I think this machine did. It just accepted any string which had at least an A or a B in it, and that was the only requirement. So fire up your regular expression equivalence checker to see whether these two regular expressions are equivalent, and if not, it means I've either made a logical error or any one of these possible tiny errors in doing this. I'm actually kind of interested to hear what the solution is. Woo! Alright, this video is not going to be heavily watched, I suspect, and I can understand that. Let's finish this off. The last two problems are actually really awesome. 9 and 10 are presenting like actual kind of thinking challenges here, and you could say that this almost should have been, part of the text. And maybe I'll write something down, or maybe I'll just talk them out. What does it say? It says, okay, first of all, some notation. Let L be a language over a certain alphabet. So I'll write this down. Let L be a language over alphabet sigma. Okay? So sigma would be like AB or something. So the complement of L, the complement of L, which is denoted, L complement, is just the set of all strings that are not in L. So it's just simply sigma star minus L. I mean, it's all the strings from that alphabet that are just not strings of L. Okay, so taking that definition, here's a theorem. This is number 9. So the last part of this homework assignment. If L is a regular language, then L complement is also a regular language. And then it just says a bunch of crap. Good. Yeah. So this is the theorem. The theorem, if L is regular, then L complement is regular. Okay, maybe this is just like totally obvious to you, or maybe it's not, but I'm just going to tell you the answer right now. If L is regular, then based on what we've accomplished this week, there is a deterministic finite automaton which recognizes L. Now, do the following. L, this finite automaton, is going to have a certain number of states. Some of those states are going to be accept states, and some of those states are not going to be accept states. Well, simply take that machine and swap the accept state status of every single state. In other words, take your machine and just let every single state in that machine that wasn't an accept state, in other words, that would be a state where the string would die, and make it an accept state, and vice versa. And now, so for every, maybe this does require some kind of picture, if this is, if I have some machine M, and okay, let me call this something like, L, la 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 la. Let's call this language L star, and this is L star. So if I have a language L star which is regular, then the complement of L star is regular. That's the theorem we're trying to prove. Well, if the language of some particular machine is L star, so in other words, take a machine such that the language that machine recognizes is L star, and now what is that machine going to look like? Well, it's going to have, it's going to have some states, and there's just going to be a bunch of states or whatever. So if that's an accept state and that's an accept state, and say those two aren't, then what is a string going to do inside that machine? Well, a string is going to get processed, boom, 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 and then it's either going to land in an accept state and it's going to be accepted, so that'll be a string of the language, that'll be a string of L star, or the string is going to complete its processing in a non-accept state, and then that string will be rejected. Well, if you now just make a new machine where these two are accept states and these two are not accept states, then you've precisely programmed your machine to reject every string that M accepted and accept every string that M rejected. And that is going to be a machine that is going to precisely accept these strings. So this machine recognizes the complement of L. Okay, this is great. Finally, show that the intersection of any two regular languages is regular. Okay. Use De Morgan laws, blah, 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 blah. So many things. Okay. Do I really need all that? Well, I guess it's something like this. I haven't actually thought this through, but so complementation has this property that if a language is regular, so is its complement. What about what are we doing? The intersection. What about the union? Well, the union I can do as well, right? If L1 and L2 are regular, then certainly the language L1 union L2 is regular. I shall talk this out, but I think it's pretty clear, right? Because well, what do? If these are both regular, there are machines which there's a machine which recognizes all the strings of this language, and there's a machine that recognizes this language. Well, now just make a new machine where you have an initial start state and you just split the machine in two non-deterministically into two smaller machines, and you just run that string through each of these machines, and if it accepts either of them, then we accept. Okay, so taking that as kind of a background, now we get to the real theorem that we're supposed to be proving, which is that if L1 and L2 are regular, then the intersection is regular. Then L1 intersect L2 is regular. Okay, well now this is somehow harder because you need this new machine to accept the string if and only if the string is accepted by both of these machines. And that's not so clear how to do that. But okay, De Morgan's laws to the rescue. Because I guess, how do I want to say this? L1 intersect L2 is just, fact of set theory or something. Just the complement of L1 complement union L2 complement. Is that true? That's probably got to be true, right? So the intersection of these things, you take everything that's not in L1, yeah, maybe just draw a picture or something, right? If this is L1 and this is L2, but this box is all of the strings of the entire, over that entire alphabet is this box, so sigma star, then L1 intersect L2 is going to be this stuff, and that's what we're looking for. But instead, if you take everything that's not in L1, so, and everything that's not in, together with everything that's not in L2, and you take the complement of that, then yeah, of course that's just true. This is just basic set theory. Okay, so anyway, now this theorem is done, right? Because to show that L1 and L2, the intersection of L1 and L2 is regular, we just say, okay, take L1 and L2, they're regular. That means there are machines which recognize them. Well then, by number 9, there's a machine that then L1 complement is regular, and L2 complement is also regular by our argument from number 9. Their union is regular by that sort of argument I just made, and then the complement of that is also regular. So the regular languages are kind of closed under complementation, union, and intersection by this process. Okay, goodbye.